Good morning, everybody. Myself, Acharya Vishvendra, and today I'll discuss OST physics, and the first chapter is motion in a straight line. So, first of all, let's have an analysis of the chapter summary. So, this chapter is comprising of certain topics like position, then we have velocity and speed, then acceleration, then equation of motion, and then applications of all of this. So, this is the chapter summary and the topics. So, let's start with the position. So in the position, the first thing is it is related to the position vector R. This is the first point regarding position. Second point is, suppose there is a point P and it has coordinates x comma y comma z, and here is the origin of the coordinate system. So I draw position vector from O to P and name it as vector R. So vector R here is x I cap plus y j cap plus z k cap in terms of 3D representation. So this is a 3D representation of the vector. I am skipping the derivation over here because it's the part of mathematical tools, vectors. So you can refer to position vector, the concept of position vector for the details. Here I'm just, making points which are directly applied in the concepts. Second thing is that if the position vector makes angles alpha, beta and gamma with the coordinate axis, then we have cos alpha as x by r, cos beta as y by r, and cos gamma as z by r. And these are called direction cosines of vector r. So here cos alpha, cos beta and cos gamma are the direction cosines. And the good thing is that if you square these and add, it will be equal to 1, and for sine square we have 2. So these are the analysis for some points. Let's move further to another dimension, which is a dimension in a straight line. So if the motion is taking place in a straight line, then we use sign convention. Generally we use take the some point as the origin, and if something is to the right of origin, we take it as positive, and if something is to the left, we take it as negative. For example, here there are two coordinates x1 and x2. Distance from origin is 4 and 3 respectively. But if we draw the position from O to P1, it will be rightward. So we take that as positive. And if we draw position vector of x2, it will be leftward. So we write the coordinate as -3 meter. So this is the application of the standard sign convention. Then point number 1.5, we have displacement. So suppose a particle starts moving from A, it follows a curved path and it moves to B. So if we draw a vector from A to B, that we call as the displacement vector, and it is equal to the final position vector minus initial position vector. Here it is your initial position vector and it is your final position vector. So this is the displacement vector over here. Another important thing regarding displacement is that it has a magnitude equal to the shortest distance between 2 points. So that's another point regarding the displacement. Then we have another application of this. Suppose the position vector of A is x1i plus y1j plus z1k, and for B it is x2i plus y2j plus z2k. Then displacement from A to B is given by RB minus RA, which will be simplified to x2 minus x1i cap plus y2 minus y1j cap plus z2 minus z1k cap. And this is called displacement from A to B, and it is equal to the final position vector minus the initial position vector. Then if we write the magnitude of this displacement, it's equal to root under x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Then is another question, which is the distance. So distance is the actual path length traveled by a particle during motion. So distance is the actual path length traveled by the particle during the motion. So for example, take the example over here. Suppose the particle moves over the curved path like this. So we straight this curved path, stretching it up, and suppose it opens up like this. So the total length of this curved path is equal to the distance as shown over here. Then there are certain comparisons of distance and displacement. For example, distance is always greater than or equal to the magnitude of displacement. And another point is distance is equals to magnitude of displacement when particle travels in a straight line without change in direction. So this you can intuitively say, when the particle is moving in a straight line, then obviously the length of this curved path is equal to the length of the straight line. So distance and displacement will be equal in magnitude. There is another important application of this. Suppose a particle is moving on a circle of radius r and it moves from A to B. Suppose radius of the circle is r, then magnitude of displacement is uh, given by 2r sine theta by 2, which is the magnitude of displacement, and distance here is given by r theta. Here one important question is that theta should be in radians. So if we analyze this, if we calculate the ratio of distance and magnitude of displacement, we have theta by 2 sine of theta by 2, and theta here should be in radian. Then we have another point that the dimension of distance is equal to the dimension of displacement, which is m0 l1 t0. So it was the first video of this sort. I'll be making let's say a set of 4 or 5 videos, so that will complete the chapter. If you have any doubt, you can ask in the comment section. Thank you and have a nice day.